Measuring stars. The stars are unimaginably remote. The nearest star is the Sun, only 93 million miles away, so close that light takes only 8 minutes to reach the Earth. There are two methods on measuring the distance to the stars. The surveyor's method. The surveyors can find the distance across the river by trigonometry or by constructing a scale drawing. Next is the astronomer's method. They must use a very long baseline. If we took a photograph of a nearby star, the Earth would have moved half away around its orbit. The apparent shift in the position of the star is called parallax. A half of a total shift of the star is called stellar parallax. Therefore, astronomers measure parallax and surveyors measure the angles of the ends of the baseline.
Intrinsic brightness. We will use two terms to refer to a star's intrinsic brightness. One, related to the magnitude system, and second is refers to the amount of energy the star emits in 1 second or luminosity. Parallax in distance. In order to get the measure of the star, you first need to get its speed, arc sec, and the formula of it is d is equals to 1 over p. For example, the star Altair has a parallax of 0.20 seconds of arc. Using the formula, the final answer of it is 5 pc, because 1 parsec equals about 3.26 light years. We simply multiply the 5 pc and 3.26 light years, so the Altair is about 16.3 light years away.
Let's proceed to absolute magnitude. In getting the absolute magnitude of a star, we should use the distance moduli. This is the distance moduli. The quantity m minus mv is called the distance modulus, a measure of how far away the star is, and dpc is distance in parsec. If we know the distance of a star, we can find its distance modulus from the table. If we subtract the distance modulus from the apparent magnitude, we can get the star's absolute magnitude. The intrinsically brightest stars have absolute magnitude of -8. The faintest is about 15.
Let us know the diameters of stars. Two factors influence objects' luminosity: the surface temperature and surface area. First, we have to know the HR diagram. The HR diagram is a graph that separates the effect of temperature and surface area on stellar luminosities. Points near the top of the diagram represent very luminous stars, and points near the bottom are very faint stars. Points on the left are hot stars, and on the right are cool stars. As we see, as the magnitude increases, the surface temperature also increases.
The main sequence is the region of HR diagram from upper left to lower right, which includes roughly 90% of all stars. Dwarf stars near the bottom, giant stars are in the upper right, and supergiants are near the top. So let's proceed to luminosity. Luminosity is the total amount of energy a star radiates in 1 second, not just visible light, but all wavelengths. It depends on two things, its size and its temperature. So the formula, luminosity is equals to radius squared times temperature.
Luminosity classes are the names refer to the sizes of the stars because size is the dominating factor in determining luminosity. We can tell whether it is giant or a main sequence star. These luminosity classes are represented by the Roman numerals 1 through 5 as shown in this list. Using the letters for subclasses, we can distinguish between the bright supergiants such as Rigel and the regular supergiants such as Polaris, the North Star. We can plot the locations of the luminosity classes on the HR diagram. These are an important tool because the luminosity of a star can give us a clue to its distance.